So now we are going to, so now you see that the temperature is related to the kinetic energy of the system, right. So therefore we are going to understand what what energy means. We know about kinetic energy as half mv square, but is there other form of energy, or is it related to all other different things that we see. So it turns out that there are energies can be distinguished into 3 different types. One is internal energy of the system, another is work, another is heat. Although we will see that they are all same, but one can distinguish from the other by using certain measures. First we will discuss about internal energy of the system. Now internal energy of the system can be 2 things, kinetic energy and the potential energy. So kinetic energy plus potential energy, which we know as the total energy, in thermodynamics it is called internal energy of the system. Now kinetic energy we know that it is half mv square, but potential translational kinetic energy, rotational kinetic energy, vibrational kinetic energy are different forms of that, but potential energy is little bit complicated, and there is a lot that is hidden in the potential energy. We know very well about the gravitational potential energy, right. So let us say a object is held at certain height. So let me get a chalk. So when a chalk is held, let us say at a particular height, it has certain potential energy, gravitational potential energy. What is meant by that is that it is high compared to the ground by value of h, and therefore it has the potential energy of mgh, and this is the energy that is stored here, which means that if I release that energy, this energy is going to go to the environment. We heard the sound, so now that energy has converted to initially kinetic energy and therefore sound, and later on it also used to break the chalk, okay, and then rest dissipated to the environment. So that was the energy that was stored in that chalk as the gravitational potential energy, but there is more to it. There is molecular potential energy, and molecular potential energy is the constituent of the chalk itself. So let us say irrespective of where what the height is, let us say the chalk is lying on the ground, does not matter, or it is resting on the hand, it has a certain potential energy, and that potential energy we can say that it is a molecular potential energy, and the origin of that potential energy actually comes from the fact, comes from let us say quantum mechanics, that says that every atom or every system is constituted of atoms, and every atom is constituted of electrons and protons, and there is electron-electron repulsion, nuclear-electron attraction, and nuclear-nuclear repulsion. Once we have all those parameters, eventually one can solve quantum mechanical equation, which was actually discussed in chemical principles 1, and one can obtain the energy of the system, and that energy, as we know in quantum mechanics, we will get both the kinetic energy and the potential energy of the system. That means we will get the internal energy of the system. However, it is not always possible to solve quantum mechanical problems for big systems. Therefore, these interactions manifest in several empirical categories. We categorize these fundamental interactions between electrons and protons, and between different electrons and different protons, into several empirical categories, which is known as bonding or non-bonding interactions. So we know about that there are ionic bonds present, there is a covalent bond, we have a definition of what is covalent bond. When carbon-carbon bond in a ethane molecule will be a covalent bond, or carbon-hydrogen bond in a methane molecule. Then there is a metallic bond, and each bond will have a certain amount of energy associated with that. So this energy typically means that they are stabilized by that much value of energy, and there are non-bonding interactions is also present, where we do not have, okay. So in bonding typically will be described by if there is a electron sharing between two given pair of atoms. However, let us say electron is not fully shared, however there is certain other kinds of interactions like ion dipole interaction, hydrogen bond is another type of interactions, non-covalent, dipole-dipole, ion-induced dipole, and dipole-induced dipole, and dispersion type of interactions. So as you see that they are empirical understanding of what is going on much, more fundamentally in quantum mechanical level. And once one categorizes these particular interactions, one can understand that how much potential energy is stored within a molecule. For example, this is calcium carbonate. It is a chalk, so therefore it is a calcium carbonate. So there is energy stored within this particular system. And how do we know the energy stored in the system? Because we have a way to release that energy from this, right. So we are going to do that in a moment. Yeah. So we are going to release the chemical energy stored in the chalk to outside. Do you have an idea how to do that? Correct. Okay. So this is calcium carbonate and this is sodium hydroxide. So this is a molecule perfectly stable, right. There is no problem with any of these two right now. And what do you say about the potential energy of the system? We don't have any idea what the potential energy of the system is right now, but there is energy hidden within this, and this hidden energy can be released when we do some chemical reactions. Then this will be converted to something else. So before you do that, which water are you going to use? We are going to measure the temperature, and we are going to use this one quickly. So let us use the hot water. So again the temperature remains to be 35.6, is getting cooler because of the atmosphere. Raman is pouring the water and sodium hydroxide. We are going to start it, right. Yeah, let it equilibrate and pour it here. Okay, let me pour on the calcium carbonate, right. Getting hot. So yeah, I can feel the temperature from outside, but I will just measure it by my infrared thermometer. It is 59 degree now. What was there in the bond between sodium and hydroxide ion, because water separates them, it is releasing that energy. So we are going to show you by an example of that. So here I have drawn a particular potential energy profile. So y axis is potential energy and x axis is the distance between these two particles. So when the distance between two particles is actually large, here I am showing it here, but let us say two particles distance is this much, let us say this is the distance, then the potential energy is actually higher. As these particles will come closer and closer, what is going to happen is potential is going to decrease. So when the potential is going to decrease, where the energy will go? It will go to the environment. So whatever is, so it is called stabilization of the energy. So now the system has become stabilized, or system has gone to a lower energy level, the energy that was there in the system has to go out, and that is what we typically see as something called exothermic reaction. So exothermic means whatever was the energy before, that system has now become stabilized and the difference amount has gone out. Endothermic is just the opposite of that. We have to supply energy to the system and system has gone there. So this particular equation, however, we are showing two argon molecules and we are showing non-covalent interaction, and this profile is called van der Waals interaction. So even when there is no charge, there is still an induced dipole interaction which we call dispersion interaction, and those particles will interact through that dispersion interaction, and one can fit this kind of profile to understand the interaction between the two particles. So as I said, that interaction energy is delta E, potential energy of the system is minus E. So right now it has become minus E. So it was started with 0, now it has become minus E, let us say, and therefore E amount, or minus delta E, and delta E amount of energy is released, delta E released. So, this means that we need to supply energy or heat or do work to break the interaction, and this will be an endothermic process. An ideal gas molecule, as I said, has no interaction energy, and however real gas systems will have interaction energy. So, real gas meaning we will talk about argon molecules or nitrogen molecules, oxygen molecules, they will have interactions with each other, and those interactions are typically a stabilizing interaction. So, now we are giving two more examples. We have talked about ATP before as a molecular motor. So, what ATP does is that it uses water and gets converted to ADP, and the energy that is stored in its bond is being released as heat or some other energy, or when molecular motor like kinesin uses that, it uses that energy to work. And calcium carbonate example you have given that, and typically we denote that as energy versus reaction coordinate profile, where if the product is lower than the reactant, then we call it exothermic reaction, and this is the amount of energy that releases, and if it is other way around where it is higher than reactant, then that will be an endothermic reaction in which we have to supply the energy. And you will see that it will be very useful in thermochemistry later on. Okay. So, now I have a question for you, is that can you give an example. So, this is an example of a chemical reaction that we are given, right, ATP and calcium carbonate. Can you give an example of hydrogen bond breaking reaction which we can actually observe? Some example where hydrogen bond breaks. No, I am saying a physical example which we can actually show in front of you. Melting of ice, when ice melts, ice has actually, is not entirely wrong, actually correct. So, ice has 4 hydrogen bonds. When it melts, it still retains hydrogen bonds, however not all 4. On an average it retains 3.6 hydrogen bond, it is not 3 also. So, if you calculate the average, then it will be normal water is 3.6. So, you are right that from 4 it goes to 3.6. However, another example, more non-intuitive I would say, but this is a good example of ice melting. So, give me a piece of paper. Okay, so this is a paper. I have broken the hydrogen bond with sounds. So, this is again an example, and instead if I burn that, if I burn the paper, then I am going to do a chemical reaction in which after initial initiation of my light which helps it to cross the barrier for burning, it will be an exothermic process giving us both heat and light, and that is because of a chemical reaction is going to give rise to carbon dioxide. Okay. So, we understand that internal energy of 2 different kinds. One is potential gravitational potential energy, another is molecular potential energy, and molecular potential energy can be understood from different possible interactions. All will have the root of same root as quantum mechanical description. One more thing that I should emphasize is that energy that people call as mass energy, coming from Einstein's equations of E equal to mc square. So, just because of formation of this particular mass, a lot of energy has been used, right. For this much mass, one has used like huge amount of energy. For that mass multiplied by c square, c is the velocity of light. So, you can understand like it will be 9 into 10 to the power 16. I am going to multiply with the mass in order to get the amount of energy. So, do you think we can ever use that energy from the paper? See, we are using which kind of energy? We are using the energy that is stored in bonds or some other kind of non-covalent interactions. What about the energy stored in the mass? Can we ever use that? So, you can say that for radioactive or fission reactions and all, we can use that, but not fully, part of it of course, right. But other than that, in a normal place like here, if we could use this mass into energy, our all energy problem would be solved. It turns out that when you have to use that, when you have to convert the mass into energy, the process requires, or the other way around, energy into mass, the process requires enormous energy itself. And the elements that are there, that are present on earth, for example carbon, hydrogen, nitrogen, oxygen, etc., they never got produced on earth. They were produced after the Big Bang. After the Big Bang, hydrogen and helium were the two atoms that got produced first, and for all other heavier elements like lithium, beryllium onwards, it required big events like explosion of stars and supernovas and things like that to create mass from energy. So initially in Big Bang everything was energy, as I said the temperature was 10 to the power 31 Kelvin, right. After that mass has formed, matter has formed, and formation of that matter required enormous of energy. So this is a table taken from from this particular website that shows you that what kind of events created what kind of masses or matters. For example, hydrogen and helium required Big Bang fusion or cosmic ray, Big Bang fusion created hydrogen and helium, as I mentioned before, and then for lithium, beryllium required cosmic ray fission, and then and boron also, and then all this ruthenium and all that required merging of neutron stars. So when two neutron stars merge, you can imagine that the amount of energy that will be produced. That much energy is required to convert to a mass, which is not normally is never possible on earth. So therefore in thermodynamics we do not consider E equal to mc square ever into the picture as the energy. So when you talk about energy, internal energy of the system, we do not consider E equal to mc square, because that is not possible on earth. Another calculation, another thing I want to ask you is that, let us say every day you are eating something, and let us say from your childhood you have grown to this much weight, or let us say I take about my example. So when I was born my weight was 0.5 kg, right now it is 80 kg. So how much energy I must have taken in order to form a mass of 80 kg compared to 0.5? Will you multiply by mc square? So it turns out that we take normally 2000 calorie per day, and an adult person, let us say everybody takes that from childhood onwards. So from childhood onwards, if I calculate that the energy intake that I have, which is my weight is my age is 41 years, 365 days, and every day I take 2000 calorie, that much energy I have taken in my whole life. If you convert to mass, I have to divide by c square, right, equal to mc square. This will correspond to a microgram of energy, microgram of mass. So taking all that, if had it been converted to mass, all that energy, I would have gained only a microgram. So certainly that means what? That energy has not made us grow in size. What all we have done is that we have taken mass and put it inside. We have taken a rice and the content of mass, that mass we have taken it in. The energy that is required is to maintain our body temperature and do other functions. It is just the oil in the machine rather than machine itself. Okay. So with that we will end today's lecture.